Respected speaker, honorable participants, and curious minds across the country. A very good evening to everyone. Myself, Shourodip Odhikari. It is my great honor and immense pleasure to welcome you all to this enlightening session organized by Modok Trainer Academy, where we step into the cosmic canvas of mystery and wonder with our very special webinar, Our Mysterious Universe. Tonight, we are blessed to be in the presence of an extraordinary mind, a scholar whose lifetime of research has contributed immensely to our understanding of the cosmos. Respected Dr. Subenoy Chakraborty, Professor in the Department of Mathematics, Jadavpur University. Dr. Chakraborty is not just an eminent academician, he is a luminary whose work in mathematical physics, cosmology, general relativity, and quantum gravity has been recognized nationally and internationally. From receiving the Calcutta University Gold Medal to being consistently ranked among the top 2% scientists globally by Stanford University, his journey is nothing short of inspiring. He has delivered over 100 invited talks across prestigious national and international platforms and supervised more than 40 PhD students, many of whom are now leading scientists and researchers. His projects, funded by reputed institutions like CSIR, UGC, ACRB, and his insightful contributions to quantum cosmology, wormholes, and black hole thermodynamics have deepened our understanding of the universe and its secrets. Before we begin, let us remind ourselves this session is more than just a lecture. It's a journey through time, space, and thought. I encourage each one of you to keep your curiosity alive and take this opportunity to ask questions and learn from one of the greatest minds in the field. With that, let us now welcome our today's eminent speaker, respected Dr. Subenoy Chakraborty, and begin this exploration of our mysterious universe. Let the voyage into the unknown begin. Thank you all.
So, good night to all. Subenoy Chakraborty is speaking. So, uh, First of all, before starting it, I say that I don't know how I get the courage of delivering lecture on such a topic for which, as far as my knowledge goes, we know less than 1% of the information about the universe. So then how I say some words about this mysterious universe. Uh, so that is based on partially on some speculation, and then what I say from observations, because at present technology has so developed that we have lot of observations, and lastly it is purely from theoretical science. Particularly, it's a joint platform from mathematics and physics who has invented a lot purely from the theoretical point of view. So based on these three aspects together, I just prepared this lecture. I say something about this mysterious universe. Still, I say that we know less than 1% what that universe is really. So I start my lecture at the very basic level. So at first, I say a few words about our solar system. So it's just a picture from Hubble telescope that it's a what we can see, that it's a black hole. Surrounding it is the accreting gas. It's a very famous picture, and in many times you can see that picture. So I first start with that. What's the definition of the universe? So in a sentence, we can see that whatever we can see, whatever we can think, whatever we can imagine, anything, all are content within our universe. We cannot think or imagine anything beyond it. So that's the, in one sentence, I can say this is our universe. Then we always accustomed, whenever we are talking about the universe, we always accustomed with two words. One is the cosmology, another is the astrophysics. Cosmology mainly deals with the origin, the evolution of the universe, still from its birth and today and even in the future also. And astrophysics deals with any particular heavenly object, any star or any galaxy or any planet like that. If we study the evolution, its physical construction and everything, then that is dealt by astrophysics. Now, we have to imagine what is the size of the universe. So it is, I think it is a very difficult task to imagine how large our universe is. So for that, I just give you a little bit of flavor about that. First of all, I go step by step. Now, the distance that we can imagine is our measurement on the Earth. So on the Earth, we can measure the diameter of Earth. It is approximately 20,000 kilometers. So that idea we can visualize. But now I am showing you that you can imagine that how large the universe may be. Now, all of us know that we all are in a galaxy. That galaxy is named as Akashganga or Ayapoth or Milky Way galaxy. Now, that galaxy I will talk about in details later. Now, that galaxy is always approaching to another cluster of galaxies. What is the speed? The speed is 35,000 kilometers per minute. So every minute our galaxy is running with 35,000 kilometers. So in that way it is running and running, but still we cannot reach that cluster of galaxies. So now I think you have some idea that how large may be our universe. So I start with, again I am just giving one figure. So I start with our whole solar system. Now, at the very beginning of human civilization, all of us know that there, what we can see, we see that at that time we have the idea that there are 7 stars which are moving around Earth and remaining are almost fixed in the sky. Now, what are the 7? At that time, they are marked as stars. What are those stars? They are marked. They are Sun, then Moon, then Mercury, then Venus, then Mars, then Jupiter, then Saturn. So these are they termed as the 7 stars because we all see that. We see them at some point at the morning, and then at night we can see them on the other side. So it is speculated that they are all revolving around Earth. And then subsequently, Galileo, he discovered 2 more planets, those are Uranus and Neptune, by his telescope. And here I should mention that earlier we have the idea that we have 9 planets because there is another one, Pluto. But you know that around 2013 or 14, around that, the International Astronomical Society, they have rejected they have rejected Pluto as a planet because every planet has to satisfy three criteria. Pluto satisfies the two of them, but one is not satisfied by the Pluto, so they finally decided that Pluto cannot be considered as a planet. But very recently, there are some observations from which what I say astrophysicists are speculating that maybe there is another one or more planets maybe in our solar system. But it is only at the observational level, at the very basic level. So we have to go a long journey, whether for before declaring that we have at present 8 planets, maybe more than 8, 9 or 10 planets maybe. Okay, so we have to wait for that. So that's the idea at that time, that all these are moving around us in circular thought. But then they have stuck at that point. They have observed that there is a retrograde motion of Mars. So that could not be explained by this simple theory. So they then thought that something is wrong in our speculation. So then Kepler and Copernicus, you know that these were very renowned ancient astrophysicists. They came out with a novel idea. According to them, that all the planets, that means the what I say, all the 8 planets that we have, including ourselves, are they are moving around Sun in an elliptic orbit. And that's the idea first came out from them. And then subsequently, this was supported by Galileo through observation with his telescope. And then Newton came forward with some analytic derivation or some mechanical results, mathematical results he have derived for describing the motion of the planet. And now it is well known to us that all these 8 planets are moving around Sun in an elliptic orbit, and Sun is one of the foci of that elliptic orbit. So that's about our planetary systems. And also I have to mention here that these planets have some satellites. For example, Moon is the satellite of our Earth, and similarly other planets also have satellites, and they are moving around these planets. And also there are some asteroids and meteors. Asteroids are moving randomly in space, and meteors are those who are sometimes coming very close to the Earth. Again, I am giving you some idea about the distance and how long in the elliptic path the planets take to revolve around the Sun. Now, one thing is that the distance of Sun from the Earth, it is roughly around 1.5 into 10 to the power 8 kilometers, whereas the Neptune, the largest, farthest one, whose distance from the Sun is 45 into 10 to the power 8 kilometers. But one thing is that Earth takes 1 year to revolve around Sun, but Neptune takes 165 years, 165 times that than the time taken by the Earth. So distance is not 165, but as we are going further and further, the time becomes slower and slower, or it takes more times. So that is exactly in accord with the Newtonian gravity theory we know. So according to the Newtonian gravity theory, we know that gravitational force is proportional to the masses, product of the masses, and inversely proportional to the square of the distance. So if you impose that formula, and you can calculate the time period, and the time period are exactly in accord. So we can say that if we consider the planetary system, the Newtonian law is a very beautiful theory for describing the motion of the planets. So now we are coming to the stars. So gradually we are approaching. So now we are coming to the stars. sun is a star, we know. Now, how the stars are formed. Now, most of the stars, they are formed of gases. And the gas is mostly hydrogen. There is a little amount of helium and other gases. Now, these gases, they are confined within the spherical region due to the gravity, because gravity is attracting. That's why this gas is confined within a spherical surface due to the, and these gases are heavier and they have the gravitational attraction. That's why they have a tendency to contract themselves, because gravity is attractive. That's why they have the tendency to be contracted. So if we contract something, then there is a increase in density, increase in temperature. So here also the same case. So there will be an increase in temperature. For example, you can note that at sun, if you calculate the temperature at the outer surface, the temperature is around 6,000 degrees centigrade. But if you go to the center of the sun, their temperature is enormous. It is around 1.5 into 10 to the power 8 degrees centigrade. So there is a huge difference of the temperature. And as we contact this gas due to gravity, so there is a rise in temperature. If the temperature gradually rises and it goes to few thousand degree temperature, then hydrogen atoms are breakdown. That means hydrogen, the electrons come out of the nucleus. So come out of the atoms. So then as gradually the temperature increases, so then quantum effect also comes. So here two things are going on simultaneously. Due to contraction, temperature increases. As temperature increases, it goes to few thousand degree centigrade. Then what atomic reaction starts. So due to atomic reaction, the atoms from hydrogen atoms, electrons are come out. And again, due to contraction, if the temperature increases, quantum effect also come into action. And due to quantum effect, what happens? As electrons and protons are now free, two protons combine due to quantum effect. When two protons are combined, they form a new atom. That particle is known as deuterium. And deuterium consists of one proton and one neutron. Though two protons are combined, but due to quantum effect, it converted to one proton and one neutron. So it is a deuterium. And again, two deuterium atoms combined, they form the helium nucleus. So in helium nucleus, all of us know that there are two protons and two neutrons. And now, combination of two deuterons gives us a nucleus of helium. So due to this quantum effect, the hydrogen atom breaks and they form a helium atom. But here, there one thing happens. You know that the mass of a neutron is slightly smaller than the mass of a proton. So whenever we are forming the helium, which consists of two protons and two neutrons, so as there are two neutrons, but originally we have started with four protons, so some mass is lost. Now here, Einstein's special theory of relativity come into action. Because according to Einstein's theory, we have the famous equation that E equal to mc squared. Energy is proportional to mass. So whenever there is a loss of mass, it implies that there is a loss of energy. So some energy is lost. Now how that loss of energy comes into action? Now this loss of energy now come out of the star, and this come out in the form of radiation. And that radiation gives us light, which you can see, because the light we are getting from the sun, that is actually due to this atomic reaction. Because in sun, the hydrogen is burning due to this atomic reaction and this quantum effect, and it is converted to helium. And this energy loss is coming out from the hydrogen in the form of energy, and it is in the form of radiation, and that radiation gives us light, and that's why in the daytime when sun is at our at our overhead in the sky, we can see it is a luminous. We have the day. That's why. So, and that is not only for the sun, it is true for all stars. But the question is that then why we cannot see the full luminous, the other stars, because they are much larger distance from us as compared to the sun. That's why we cannot see them so luminous as we see the sun itself. So due to atomic reaction, we have that, and whenever the energy coming out from the atom, so they gives an outward pull. So previously we have seen that gravity is giving us an inward pull, and this quantum effect gives us the energy loss. So energy coming out of that, and as a result there is a external outward pressure. So this gravity contraction pressure and this quantum gravity pressure, they balance each other. As in the sun, because sun is now in a stable configuration, and most of the stars we see in the sky, they are all in stable configuration, and that's why we're in the maintaining equilibrium, and that we are seeing them in that. Now there is a question of color, but this radiation, the color of the star that is coming out, so that has some that light that depends on the color of that. That means light coming out. It also depends on the mass of the star. More the mass, then that will be more the gravitational force. If gravitational force is more, then contraction pressure is more. That's why there is a higher temperature. If higher temperature, then we have more quantum effect. As a result, we have that the temperature is higher, so color gradually changes. How changes? Now, if the mass is lesser, then it will be reddish. Then it converted, if mass is gradually increased, then it is orange, and then finally it is blue. And we can observe that in the sky also. If you observe in the sky through telescope or even in the naked eye, you can see that we have some heavier star in the sky, and that is not too far from us. One is Ovidit. That Ovidit looks as blue. And also we can see a less heavier star, which is Rohini, that we can see as red. I am just giving a diagram. In the top one, it is Ovidit, it's reddish, and here it is Rohini, that is a reddish one. So these two stars are like that. It depends on the mass, because Rohini is less mass, that's why its color is red. But on the other hand, Ovidit has more mass, so it has more gravitational pull. So that's why it has more higher temperature. That's why its color is blue. And one thing is that it is by observation, the astrophysicists have speculated that how long the sun is going through this atomic reaction. That means conversion of hydrogen into helium. So sun is doing this work for the last 450 crores years, 4.5 into 10 to the power 9 years. How long it will continue to do that? It is calculated that the sun will do that for nearly 500 crore years, for the next 500 crore years. So one way we can say that we are safe, because we are almost at the middle of this atomic reaction. So we are safe, we have no worry about that the atomic reaction of the sun will stop and what will be the consequences. So we don't worry about those things at present. Again, now I am coming to, if atomic reaction stops, then what will happen? Whenever the atomic reaction is not there, again, due to gravity, there will be contraction. So again, there will be inward pressure. So again, density increases. And now interesting is that what will be the fate of the star? So it increases. The inward pull it gradually increases. So now, what will be the fate of the star? That depends on its mass. Now, how it depends on the mass? Now that I am speaking now. Now, due to high density of the gas, there is a quantum effect. Again, it comes into the picture because it gradually contracts, means the density gradually becomes larger and larger. So here, then, electron-like particles, they have some peculiar behavior at that time due to the quantum effect. They don't like to stay side by side. Two electrons don't like to stay side by side. So they always repel each other. And this repulsion of two electrons or number of electrons which are there, free electrons which are there due to dissociation of hydrogen and proton in the hydrogen atom by atomic reaction. So they dissociate. And as a result, there is a repulsive force. And that repulsive force again results in outward pressure. And that pressure balances the attraction of gravity or inward pull of gravity. This pressure that is created due to the repulsive force due to the nature of the electron, that is known as electron degeneracy pressure. And this electron degeneracy pressure that balances that inward gravitational pull until the mass of the star is less than or equal to 1.414 solar mass. So if the mass of the star is not too large compared to our sun, then it will be electron degeneracy pressure balances this gravitational pull and the star will remain in this equilibrium state for infinite. So here I must mention that sun will be also balanced by this electron degeneracy pressure in future. And further, here we should know that this mass limit, that is 1.414 solar mass, for which the star is balanced in an equilibrium position by the electron degeneracy pressure, that was calculated analytically by our Indian physicist Subramaniam Chandrasekhar, and for which he got the Nobel Prize. All of us know that Chandrasekhar got the Nobel Prize and he calculated that. That's why this is known as the Chandrasekhar limit. And these stars whose mass is less than 1.414 solar mass, they are known as the white dwarf stars. So white dwarf stars, and they are much smaller compared to a normal star because they contracted significantly, so that's why they are much smaller compared to these. Now, sun will be a white dwarf star, then, and it will be obviously contracted. The question arises that at that time, when sun will be a white dwarf, what will be its radius? Now, it is calculated that at present, the radius of the sun is roughly 100 times the radius of Earth. So its volume is 10 to the power 6 times. But when sun becomes white dwarf, then its radius will be nearly the radius of the Earth. So it is just theoretically calculated. I have given you a schematic diagram of white dwarfs. But what will happen if mass is now, we are coming to the other inequality, that if mass is greater than 1.414 solar. In that case, the gravitational pull will be larger. So electron degeneracy pressure cannot prevent that gravitational pull. So again, there will be contraction. And due to this contraction, again, the quantum effect come into action. And when this quantum effect come into action, then what will happen? Electron and proton, those are now free. They will combine and they will form the neutrons. So neutron will form quantum mechanically by combination of electron and proton. And then these neutron have identical behavior as the electron. Two neutron cannot like to stay side by side. So again, there is a repulsive force. And Due to this repulsive force, the gravitational attraction is balanced. And then those stars are known as neutron stars. And the pressure created by this repulsive force due to neutrons, those are known as neutron degeneracy pressure. So again, we have an equilibrium state occur, and that also stays for an infinite time, and those stars are known as neutron stars. And obviously, we can speculate that these neutron stars will be much smaller in size than the white dwarfs, but they have tremendous, enormously large density, because they are within a very small area or small space. It is a tremendous amount of mass is there, so density will be enormously large. So also they are in a stable configuration. But here the question, this is the schematic picture of neutron star, but here the question is there any upper limit for neutron star? Because we have the lower limit. Because if the mass is greater than 1.414 solar mass, then we have the neutron star. But is there any upper limit for neutron star? The answer is not here. Not exactly exact result as the white dwarfs. We have no upper limit so far. So it's a very challenging issue. And if there is in the audience there are young minds, I just request them try to do that, because it will be also a very marvelous one. But what we can speculate is that if the mass limit is greater than, almost greater than 3 solar mass, then again the Newton degeneracy pressure is not sufficient to balance the gravitational or to counter the gravitation. So the contraction will going on, because neither electron degeneracy pressure nor Newton degeneracy pressure can prevent the gravitation or counter the gravitation. So contraction going on. So, and star gradually becomes smaller and smaller. So at one stage, it happens that even light cannot coming out from that, because due to the strong gravitational pull, the light cannot coming out, the path of the light ray bends, and it again goes inside the sun. So if light cannot come out from any object, we cannot see that object. So at one time will come when we cannot observe that star, because that will be totally become invisible. So that stage of the star is that termed as the black hole, because we cannot visualize. So there are 3 end state of the star. One is the white dwarf, second one is the neutron star, and third one is the black hole. So these are the 3 ultimate states of a star at its end state. So that's the figure of a black hole we have seen. This is the at the center position where it is totally black, because light cannot coming out of that. And here there is an accretion disk, or it is a jet coming out from that due to the X-ray emission. So these are the some astrophysical issues I just show you in the schematic. Now, most of the stars which we see in the sky, as I have already mentioned, they are also in the atomic reaction state, and they radiate light that we can see them in the sky. And ultimately, they have these 3 end states. But one thing I should mention, that there is an interesting intermediate state of the stars. What is that intermediate state? For less heavier stars, that means stars of the form of white dwarfs, there is an interesting state. What is that state? Now, when the atomic reaction ends, then stars started gradually contracting. But its center gradually contracts, but its outer part, that will again expand. And it becomes enormously large. And the color of the outer part almost gradually becomes from yellow and then reddish. It becomes reddish. Whenever sun as becomes a white dwarf, then its outer part expands so largely that its outer part enters into the orbit of Mercury and Venus. And then the temperature is so large that no life is possible on the Earth's surface. So whenever sun have this situation, so life is challenged on the Earth's surface. And subsequently, what will happen? And subsequently, it happens that the outer part gradually expands and then it absorbs in space. So then we can see only a ring of that. And that is visible in the sky. You can see that there is a ring-like star near the star OVG that we have mentioned, and that is termed as Niharika. And we can see that starts with the red giant-like star. We can see in the sky, those are known as Jesta, the Rohini, like that red giant star we have seen. So that is for mainly for white dwarfs. But if the star is neutron star or black hole, the situation is completely different. If the star is neutron star or black hole, they have more mass. So they have more mass means they have higher temperature. And as they have more mass and they have higher temperature, when the electron burning is completed, then it starts again another atomic reaction because it has more energy. Then helium is acted as a fuel for atomic reaction. Previously, hydrogen acts as a fuel for atomic reaction. After hydrogen converted into helium, then helium takes place of the hydrogen and he acts as the fuel for further atomic reaction. And then if helium is act as the atomic fuel, then we have higher order elements are formed. So subsequently, for those massive stars, so hydrogen is converted into helium, then helium is converted into carbon, then carbon is converted into nitrogen, nitrogen is converted into oxygen, then sodium, then magnesium, aluminum, and in those way it continues until it is iron. So up to iron, this atomic reaction continues for massive stars. But whenever iron is raised, the atomic reaction will stop. Why? Because we already mentioned in all these atomic reactions with hydrogen, helium, carbon, nitrogen, oxygen, so on, in all these cases, whenever the next higher element form, there is some loss of energy. And that loss of energy radiates out and we see the light. But whenever iron comes, then the combination of two iron elements, when goes over some other complex elements, heavier elements, then some energy is required. Instead of losing energy, it requires energy. But from where it gain energy? There is no source of energy. So atomic reaction stops at that case. And whenever atomic reaction stops, there is no outer pressure. If there is no outer pressure, then gravity contraction again starts. But it is a heavier one. So gravity contraction starts very rapidly. But there is heavier elements are there, and it is to be remembered that these heavier elements are stays at the outer core of the star. And there is a huge random motion occurs at that stage. And due to this huge random motion, this contraction of the star, there is a huge random motion, and this huge random motion, there is a tremendous random motion, and all particles at the outer surface, they come out at the outer part, they explode. And they explode with a tremendous speed. So these various elements which are formed on the inside at the core of the star due to this atomic reaction, they spread out all over the universe. As a result, this outer part gets randomly out, but there, due to this explosion, there is a huge generation of energy. And this energy then supplies the actual energy needed for atomic reaction to the iron. As a whole, at the core of the star, atomic reaction again starts because iron is there. then iron is converted to heavier elements like gold, silver, nickel, cobalt, mercury, like those things. And again, they are spread over the universe. So this explosion, due to this contraction and due to this random motion, that is termed as supernova explosion. So astrophysicists have discovered that because there is a huge luminosity suddenly occurs in some part of the sky, and that is often occur in the sky. Physicists are often, and that can be seen in the naked eye also. You can see that. And what is the brightness of that supernova explosion? It is equivalent to few crores of stars. You just imagine that if you collect the brightness of few crores of stars, that luminosity is equivalent to one supernova explosion. But interesting thing is that this supernova explosion is responsible for the life in the earth, because you just note that all the elements which are necessary for our life, that means carbon, which are in our body, oxygen in the air, and all other things we are getting due to this supernova explosion. So interesting thing is that earlier there is no elements like these, only hydrogen. But then whenever star forms, then this starts by atomic reaction, gradually forms helium, carbon, nitrogen in that way. So all the heavier atoms are formed by the atomic reaction inside the star. And suddenly that mechanical process, that whenever gravity is contracting, there is a huge explosion of the random motion, the outer part explodes of the supernova explosion, and all these elements which are essential, which we see on the earth, they are formed inside the core, now spread over the universe, and we can see them all. So our solar system, Earth, Life, all are created from the remnant of this explosion. Okay, now these heavier stars. So one thing we should know that these heavier stars have more internal energy and radiate more energy and light than a normal star. So heavier stars uh, have died much earlier than due to the supernova explosion than a normal star compared to the sun. So those stars are more heavier, means they are shorter life, and the stars who are more less heavier, they have the longer. So this is the life cycle of the star's life. You can see gradually that sun-like star, then red giant, and then white dwarfs, and then ultimately the black dwarf, because when it is invisible. Or if it's the red giant star, then red supergiant, then there is a supernova explosion, and then either neutron star or black. So that is the total life cycle for the star. So that's the evolution of the star. But how stars are created? So that's a big question. And answer is no definite answer still yet. But what astrophysicists have speculated, I just tell you. Now, it is speculated generally that it is overall a general speculation that we see the stars, but in between we see totally dark. It is speculated that in between regions of the stars, it is not void, but they are full of either gas or dark particles. Now, this gas is sometimes it is hot if it is very close to some supernova explosion, or if it is on the other side, then it is cold. But the gas is clustered and they form a clouds. And in some places, they are moving randomly. And these clouds are heavier than this glass, and they have no light, because that's why we cannot see them. So they absorb light, but they are not reflecting or emitting any light. That's why we cannot see them. But these clouds, that's why these clouds are non-luminous. And that's why they are known as molecular clouds. And astrophysicists have speculated that stars are born into these cosmic clouds. And how they speculated that? Now, interesting thing is that you know that there is infrared light, the light which has wavelength much larger than the red light. So those cannot be absorbed by these atomic clouds. So these atomic clouds cannot absorb that. As a result, by the technological development, astrophysicists are taking photographs of the inside of these atomic clouds by these infrared lights. And they are now analyzing this inside picture of these atomic clouds. And at the very initial level, they are they have said that probably the early birth of the stars are inside this core of this atomic cloud. Though the results are at the very initial level, but they are very optimistic that they are getting the correct result that stars are born inside this atomic cloud. So I think for the next 5 to 10 years, we have a very clear picture about the birth of the star. So far now, we have a very clear picture about the evolution of the star, but we have not the picture about the origin or birth of the star. Picture is not so clear, but intuitively it is speculating this based on those observational results due to this infrared light. They are taking that probably stars are born inside this molecular cloud. So now I am coming to our galaxy. Now, our galaxy, how we can observe or how we can speculate that. If we just observe to galaxies, we have to make some change of unit because now we have to travel a large distance. So far, we are traveling a few light years distance only. Now we have to travel more and more distances. So for that, we have to make one unit of measurement of distance. So that distance we are termed as by the astronomer as the parsec. 1 parsec distance means 3 light years. You imagine that light travels 180,000 feet per second. So for 3 years, the light will travel the distance that it travels. That enormous large distance we termed as 1 parsec. It is nearly 30 lakh crores kilometers. Now, the average distance, if we calculate the average distance between 2 stars, it is few parsec distance. For example, if we see our sun from few parsec distance, then we can see 2 stars on 2 sides. On one side there is Lubdha and on other side there is Subenoy. Also, we can see that there are hot clouds in between. That means between sun and Lubdha or sun and Subenoy, there are some hot gases. From where this gas comes? This gas comes from some cluster of stars slightly far away from our sun. Now, if we go further distance, that means few thousand parsec distance, then what we see? We see that there is some molecular cloud. The size of that molecular cloud is around 100 parsecs. And we can see there a cluster of heavier stars all around the sky. And one can see such heavier size molecular clouds and clusters of stars behind Lubdha, because on one side of the sun is Lubdha, I have mentioned already. So behind the Lubdha, we can see these huge clouds of molecular clouds and clusters of heavier. And on the other side of there is hot gas, and due to the supernova explosion and the remnant, those can be visualized in the sky, and that is towards the constellation Vela. And if we go further distance, then the interesting thing happens. We can see that our solar system, it belongs to an environment That environment is like a gramophone recorder disc. It is like a earlier gramophone recorder disc. It is like that. But the center in the spherical form. It is like a sphere. And our solar system is within that gramophone recorder. And from the center, there is few hands and legs are coming out. It is like an octopus. And our sun or solar system belongs to one of the hands. And our solar system belongs to one end of that gramophone record. How many stars and constellations are there within that gramophone? Nearly about 10,000 crores of stars are there within that gramophone. And this whole system of constellation of stars with the center as a gear, as a sphere, that whole system is our galaxy, our Milky Way galaxy, which we termed as Chayapot or Akashganga. Now, our sun is how much distance? It is around 8,000 parsec distance from the center. And the solar system is, as I have mentioned, it is almost at the extreme end of our galaxy. And the interesting thing is that in spite of the molecular clouds, we have a cluster of stars we can see near our sun in the gramophone recorder that is like the calculus. Because from the very child days we have that idea of calculus. I have shown the figure here. It is just like with an arch and like that. That figure is within the gramophone record, that is within a part of our galaxy. But in the galaxy, some interesting things are happening. It is speculated that at the center of the galaxy, which looks like a sphere, it is a supermassive black hole. It is a highly gravitating object which attracts everyone. And due to its attraction, all other constellations are moving around the constellation. Now you think about the planetary motion. I have mentioned there the planets which is very close to the sun, they are moving faster. And the planets which are far away from the sun, they are moving a little bit slower. But interesting thing here in the galaxy is that all these constellations which are moving around this supermassive black hole, they are moving almost at the same speed. That's a strange thing because that cannot be what I say, that cannot be interpreted or that cannot be justified by the Newtonian gravitational theory. Because according to the Newtonian theory, the velocity of rotation that should decrease as we increase the distance. Because force is proportional to the 1 by inverse curve. So if R is increased, force decreases as well as the velocity will also decrease. So then they speculate that Newtonian theory is no longer holds there. So, but scientists come out, astrophysicists come out with a new idea. They then speculated that molecular clouds idea. They then speculated that not only these around 8,000 crores of stars are there within the gramophone record tape there, but they have speculated that in between there is a molecular clouds or some unknown matter is there, and that is responsible to that. So that molecular cloud or unknown matter, that is invisible matter, that is spread over throughout the gramophone record. That mark is known as the dark matter. So we don't know about the chemical composition of the dark matter. We know any other physical property of the dark matter. Only thing we know that it cannot radiate light, it absorbs light, and it has the attractive power as the visible matter also. So otherwise we don't know anything about it. So astrophysicists are speculating that in the void region there is dark matter, and which is responsible for this velocity remains almost identical for other stars. It is irrespective of the distance from the center of the galaxy. Now, what is the mass of that galaxy? The mass of the sun is around 2 into 10 to the power 30 kg, and mass of the galaxy is 1.5 into 10 to the power 11 times the solar mass. So it is enormously large, obviously, because there are so many constellations. Now we are going outside the galaxy. If we go outside the galaxy, I think my time is not much, so I am in hurry. So go outside the galaxy, then we can see two smaller galaxies. And how much distance it is? Few parsec, few lakh parsec distance, but they have no definite shape. And one is termed as the big Majorana, and it is known as the small Majorana. And they are almost the gravitational attraction of our galaxy. And if we go around 10 parsec distance, then we can see our neighboring galaxy, that is known as the Devjani galaxy. It is around 7 lakh parsec distance from us, our galaxy, and it is also like the Serpentine galaxy as our galaxy also. Both are. And usually the galaxies are mostly of two types. Either they are ellipsoidal or they are serpentine like our galaxy. And there are some galaxies like Majorana which have no shape. And it is, they have observed that, it can be observed that around 2 dozens of small galaxies are there surrounding our Milky Way galaxy and Devjani galaxy. And astrophysicists have termed this whole system as a local cluster of galaxies. And this local cluster of galaxies is going through a super cluster of galaxies, where these galaxies, that galaxy is around 1.5 to 2 crores parsec distance from us, and it is around the Virgo galaxy cluster. So our galaxy cluster is going towards that galaxy at a speed of 600 kilometer per second, or around 3500 kilometer per minute, like that. So it is moving around that. This is the Virgo supercluster galaxy. I have just given a rough sketch of that. And interesting thing is that now, due to the technological development, we have now optical telescope. What's the utility of that? Through optical telescope, we can simultaneously measure the distance of several galaxies. So astrophysicists have planned to have a map of this galaxy. They have planned to map that around 1 lakh galaxies. So they have mapped that. They have nicely mapped a galaxy of 1 lakh galaxies with our galaxy at the center. And how long distance they can go with that optical telescope? They have observed galaxies at a distance of 500 crores light years. I don't know, we can imagine that distance. 500 crores light years that we have observed a galaxy at that distance. And they have nicely gave a map of that. The interesting thing is that in that map, they have observed that if we consider the scale around 10 to the power 8 to 10 to the power 9 light years, then you can see that all these galaxies are homogeneously distributed around us. So that is, in cosmology, is termed as homogeneity of the space-time. So it's a very basic assumption in cosmology, and that is observationally supported by this optical telescope map. So our universe, over that scale of 10 to the power 8 to 10 to the power 9 light years, it is homogeneously distributed. So, and we have no, but beyond that, 500 crore light years, we don't know what happens. And lastly, I just finish with an idea. I just skip this thing because uh, our universe is expanding and all these galaxies are gradually receding from each other. But in the past, they are very close to each other. So if we go more and more into the past, so they are coming more closer and closer to each other. So at one time, we are to a point that is the birth of the universe, beyond which we never imagine. And that point is known as the Big Bang. And this theory is known as the Big Bang theory. So from that point, our universe evolves and it is evolving gradually, and the geometry of the space-time, the physical evolution of the space-time, all are mathematically calculated using Einstein's theory of relativity by very sophisticated, highly technologically developed. We observe our universe, observed our several heavenly objects, astrophysical objects, and their motion, and all these are mathematically studied using Einstein's general theory of relativity, and they are nicely matched with the observation. And all of us know that in 2015 we have the gravitational waves that is detected, that was predicted by Einstein 100 years ago in 1915, and that was observationally verified in 2015. And now gravitational wave astronomy is a very growing rich astronomy, astrophysics, and lot of astrophysical concepts are now getting changed by this gravitational wave because lot of information are coming. I think for the next 10-15 years or say 25 years is I think very exciting and very interesting one for knowing some mysteries of our universe. So I think the young minds who are listening this, they have that flavor and they can join into this mysterious world. So I finish my talk just with these few lines from Tagore. আকাশ ভরা সূর্য তারা বিশ্ব ভরা পান, তারই মাঝে আমি পেয়েছি মোর স্থান, বিস্ময় তাই জাগে আমার। নমস্কার, থ্যাংক ইউ।